The goal for this video is to figure out what's the Laplace transform of f prime of t. And here, let's assume that f prime of t and its original function f of t, they are both of exponential order. So that will make sure that we will be able to get the Laplace transform of these functions. So this is something that we're trying to do, and we hope to reduce this to something that we know. The best way to do this is, let's use the definition of Laplace transform. And the Laplace transform of something, okay? This is defined as the integral, but let me write down the inside here. We are looking at this as f prime of t. This is defined as the integral from 0 to infinity e to the negative st times the inside that we have, which is f prime of t. And this integration is done with respect to t. And here, this integral here, we have a product of two functions. And well, most likely, whenever we are using the definition of Laplace, we have to use the integration by parts, and that's the case right here as well. The way that I would show you for the integration by part is, I will have to make a d column and an I column. D stands for taking the derivative, and the I is to take an integral. And we have two choices, but before that, let's also get the sign ready. So this is pretty much my setup. Okay. We are going to differentiate this e to the negative st. Okay, so let me put e to the negative st here. And then we are going to integrate f prime of t. Because this way, we will be able to get the original function, so we can reduce this back to its original function, which is f prime of t. And taking the derivative of e to the negative st with respect to t, it's pretty easy. This is just negative s e to the negative st. Don't forget the chain rule. So that's why we have the negative s right here. And that's pretty much all we need, because the more we do, the more complicated it's going to be. So this is how this works. The diagonal, the product of the diagonal like this, is the result of the integral. So for the first step, we are going to write down e to the negative st times f of t. Okay, and then this integral here, this is the result, and the original integral is going from 0 to infinity. So I have to write down, this is t, it's going from 0 to infinity. The next thing is, the diagonal is the result, so we are ready to evaluate this part already. But each row like this, each row right here, this right here, it's still an integral. The product of these two things, it's still an integral, okay? And the reason the sign changes plus minus is because if you look at the usual integration by parts formula, it's like u phi minus integral of dvu, things like that, right? That's why the sign changes. Anyways, here we have minus times minus, which is a plus, and keep in mind that's still integral, so let me write this down. We have a plus, another integral, and with the same limit from 0 to infinity, s e to the negative st, oops, let me put s right here, e to the negative st times f of t, and this is once again dt. Okay, now this part, it's already ready to evaluate. And here's the idea. We are going to plug in infinity into t, and symbolically, that's the idea. Well, let me do this for you guys. Let me make a side note right here for you guys. So we are going to take the limit when t goes to infinity, this part, and let me put down f of t on the top, over, because we have a negative exponent, I will write this as e to the positive st when t goes to infinity. And because we must have f of t being of exponential order, otherwise this limit wouldn't exist, wouldn't be 0, wouldn't be a nice number. So we have to assume that, and if we do assume that, this limit is going to be 0. Okay, so in another word, we must have this to be 0 or some nice number. Okay, so Then what we get is that here we have 0, and then we're going to subtract the case when we plug in 0 into t, and we will get e to the negative s times 0 times f of 0. Okay, so that's pretty much it. And as you can see that this part here is just going to be minus e to the 0, which is 1, times f of 0. So the 0 doesn't matter. So here we have negative f of 0, and that's the result of we plug in the infinity and 0 for the first part right here. Okay, let's focus on this remaining integrations. This integral is with respect to t, so the s right here is like a constant, so I can take the s outside. So we're adding, this right here is just s, and we have the integral from 0 to infinity, e to the negative st. So let me write this better right now. E to the negative st times f of t dt. Okay, so notice that the s is just the s, right? But if you pay attention to what the integral is right here, this integral, this integral is exactly the Laplace transform of this function, its original functions. Okay, so in another word, we'll be able to reduce the Laplace transform of a derivative into negative f of 0 plus s times the Laplace transform of its original functions. And the usual way that we like to write this is put the s Laplace of the original in the front, and then minus f of 0. And we are done. This is a very useful formula that we're going to use to solve differential equations. So now we have that the Laplace of f prime of t, and f prime is just that we are taking a derivative of f of t. This right here is s times the Laplace of its original minus the original function at 0, so f of 0. We can also figure out what's the Laplace of the second derivative of the function, because the second derivative is just like taking the derivative of the first derivative. So I can look at this as taking the Laplace of the first derivative of the first derivative. So the input here inside of this parenthesis here is f prime. Okay, and if we match the formula, this right here will be s times the Laplace of whatever you enter right here, right? And in this case, it will be just f prime of t. And let me put that down into the bracket here. So f prime of t is here. And then we are subtracting whatever we have here. Notice that we are subtracting whatever we have here. We're plugging 0 into whatever we have here. So we are subtracting f prime of 0. And that's pretty much how we can reduce from the second derivative to the first derivative in terms of the Laplace transform. But then furthermore, because we already know that the Laplace of the first derivative, it's just this, right? The Laplace of f prime is just that. So let me kind of just box these two things. So I can substitute this into that. And I'm just going to write this down. So I have an s on the outside. Let me open the parentheses. So this word right here will be, let me see, s times the Laplace of the original function minus f of 0. Then on the very outside, we still have minus f prime of 0. Okay, so this is how we can reduce for Laplace transform of the second derivative into the Laplace of the first of the original. And of course, we have a parenthesis and an s on the outside. We can distribute, and we can get this as s squared Laplace times the Laplace transform of the original function minus s times f of 0, and then minus f prime of 0. So that's it. So this will be the formula that we're going to use very often to solve differential equations. Okay,